Hi, today I'm going to talk about OVS-DPDK on Windows. I'm William Tu from VMware. So a little bit introduction about OVS. So openvswitch is a software switch like Linux bridge or Hyper-V switch. So usually the SDN controller talk to the OVS or the virtual bridge through the open flow protocol. And for OVS, we have majorly two components, one in slow path, the other in fast path. The slow path runs the OVS vSwitch, and the fast path, or we call it Datapaths, runs inside the kernel, or in the DPDK case, it runs in Userspace. So when packet arrive at your machine, the packet will first miss the data path. It go into the slow path to resolve the open flow table to know how to process this packet, for example, to drop it, forward it, or to mirror it. And then it install a cache into the data path so that the subsequent packet will go through the data path or the fast path instead of the slow path. So the data path will consist of, for example, a packet IO channel to send and receive packet. So it usually talks to the driver to get the packet IO. It's a cache for processing the packet, and it's pretty important for the performance. Today, OVS supports three different Datapath implementation. So the first one is Linux kernel. So in every Linux distribution, we have openvswitch.koll, the kernel module that implement the OVS Datapath. On the Windows side, we also have a kernel module, which is a extension. It's a Hyper-V extension, which attached to the Hyper-V virtual switch to redirect packet, to process the packet in the Hyper-V openvswitch extension, and then apply the actions. The third one, which is the one we are going to talk about today, is the Userspace Datapath. So that Datapath is not part of the kernel, but it's part of the Userspace, the OVS. So today it's used by DPDK, or recently we have been adding support for AFXDP sockets. So it's been used by DPDK or AFXDP. So Userspace Datapath with DPDK, or we call it OVS-DPDK, is pretty fast. It's basically the fastest OVS today. So the idea is that when packet comes from your NIC card, it doesn't go to the kernel. It actually bypass the kernel space, and the packet directly DMA the packet content into the Userspace OVS. So the Userspace OVS Datapath will get a pretty high packet rate due to using DPDK library to send and receive the packet. In the meantime, OVS Userspace Datapath also have several or a lot of optimizations to process the packet in Userspace. For example, we have several different caches to process packet, or batching, supporting batching to batch process, or subtable based on statistic to subtable reordering. However, this OVS-DPDK today only support in the Linux platform. So for Windows, it's not working yet. So in this talk, we are going to show you that OVS Windows can actually work on Windows. And there are several benefits. For example, the first one is flexibility and maintainability. For example, we want to share most of the Datapath code on the two different platforms. For example, if you are adding a new feature, or if you find a bug in parsing protocol, packet header protocols, for example. Today, if the Datapath runs on both Linux kernel and Windows kernel, then you have to fix at two different places. And you have to understand the two different Windows API, Windows kernel module API and Linux API. So if the Datapath is in user space, then it's basically the same code base, and fixing the bug one place will work on two platforms. And also adding new Datapath features. For example, you want to add new protocols or new flags to your new protocols, or experimenting something new, then adding these features to the user space Datapath well works on different platforms. The second one, of course, is performance. So DPDK already shows very, very good packet I/O performance by bypassing the kernel. So we'll get very high packet I/O rate at the user space Datapath, and we also has a lot of optimization for packet processing in the OVS user space Datapath. In addition, the DPDK library also, and OVS, they also support programming the hardware flow of load using RT flow API or TC flow API by just enabling like a flag in OVS-DB, say hardware flow, enable hardware flow is equal to true. So if you are running a NIC card that support flow of load, we might be able to take the advantage of doing the flow processing entirely in the NIC card instead of going to the user space and process using your CPU. So to get OVS-DPDK running on Windows, so first we have to we have some work about the build system. So Sergey will talk about it in another talk. So basically today the Windows OVS, to compile Windows OVS, we are using auto tools. But because DPDK use Meson, so we have to add support for compiling OVS using Meson. Other than that, there are some features that needed to be ported or replaced to the Windows from the Linux to Windows. So for example, if you see like today the underlib dpdk.c file, we are using POSIX open string or f open cookies to redirect the DPDK logs to OVS. However, this POSIX API doesn't support Windows, so we have to find alternatives. The second one is like vhost user protocol today is used in Linux to connect OVS to virtual machine and containers. It doesn't support in Windows, so we are looking for replacements like other PMD support. And also like DPDK stacking memory configuration is also not supported, or today when OVS start, we will detect the NUMA information, or we find out the system's CPU or memory by parsing the string in the proc file systems. So these are not working in Windows, so we have to re-implement it and these features to support it. And for more details, I have sent out an RFC patches in this link. So to compile it today, for example, in Linux, DPDK today already support Meson builds, and OVS is using auto tool. So this is a Linux part. So for Linux part, we build DPDK by using Meson. And then for OVS with DPDK, we can just say configure and then dash with DPDK equals to static or share library. For the Windows part, we add support for Meson build for both DPDK and OVS. So to build Windows DPDK, we do Meson build. There are more details in the DPDK document about how to build DPDK Windows version. For the OVS part, to build OVS using Meson and then link with DPDK, we do Meson build, and then we have to specify the path which has the DPDK build. And then it's pretty much the same, like Meson build and then Ninja. Then it will generate the exe file. So once we get the binary, the openvswitch binary, we have to find a system to run on it, right? So first we have to figure out what's the PMD support on your system or what's the device support. So today, not all of the DPDK PMD drivers are ported to Windows. So you have to look at either it's your physical machine or your virtual machines. So for example, if you have a physical machine today, it supports Intel ICE, i40E, or XGBE. If you have Mellanox, it has MLX5 support. If you are running pass-through using virtual function and runs Windows inside a VM, then you can use XGBE, VF, Mellanox, or ICE. Or if you are running VM and then with emulated software device like E1000 or VMX3, it also supported. And for different device, it has at the host side, at the Windows server side, it has different configuration set up. So for Mellanox, you have to install DevX and WinOF2. For Intel and other NICA, you need NetUIO drivers, which is similar to the UIO driver like people runs in Linux, and the Virtu2Physics driver to do the address translation from Userspace to device physical address. I have posted a demo here in link here. So in this talk, I have set up a physical test bed with 2 servers. Each one runs 12-core Intel CPU Xeon with 32 GB of memory. So I use one server as a traffic generator, which runs Linux. The other server, I run Windows Server 2018, and I have 2 Mellanox Connect 6 card connected back-to-back with 25 GB of NIC. On the Windows side, I install DevX and WinOF2. So for performance reason, I want to compare these 4 or 5 cases. So first, of course, is today's OVS kernel module on Windows. And then I want to compare DPDK L2 forward, which is the example code in the Windows DPDK. So it basically did nothing but just receive a packet from one port and send packet to another port. And I want to compare, there's another project called eBPF for Windows, and it provides a sample program called reflect packet.o. So this is more like the XDPTX option, which receive a packet from a port and then I think it parses the packet or something. It does some very minimal things and then send the packet out. And the last one, I want to try RTE flow or flow by programming the flow information, the flow into the Mellanox hardware. So to start, OVS-DPDK, it's pretty much similar than in Windows and Linux. So DPDK, of course, we have to enable it, and then hardware flow equals to true. So it will try to offload the flow if possible. If it fails, then it does the processing software. When we start OVS-vSwitch, we say disable system, which means don't load the kernel module. And then we are using dummy Luma here because the lim Luma doesn't work. So this kind of manually set the number of cores here. And then when we create a bridge BR0, we have to say Datapath type equals to netdev. This tells OVS to use the Userspace Datapath. Then we can attach the port using its PCI ID and type equals to DPDK. And then we install one rule, or we consider 2 cases. One is rxdrop, which action import equals to P0, action equals to drop. Or when packet comes in from one port, we just send it to another port. At another server which runs Linux traffic generator, we just use DPDK testp and leave, which just it has a TX only mode, which just sends 64-byte UDP packet at 4 speed. So this is the result I got. So on the y-axis is the packet rate, the million packet per second. So the first one we see is kernel. So in the case of kernel, for just simply dropping the packet, I got 2 million packet per second. For basic forwarding, I got about 1.2 million packet per second. For the DPDK L2 forward example program, it's showing much better. It's showing 32 for drop and 29 for forwarding. That's the DPDK example program. For the OVS-DPDK, which is the work we have done here, it shows both about 32 million packet per second for dropping and forwarding the packet. So this means that there are about 9 million packets, or there's some overhead of OVS processing the packet from DPDK library. And then finally, we are seeing the XDPTX, which is from the eBPF for Windows project. It's showing pretty low performance here. And for the RT flow case, I found that it doesn't work for both drop and L2 forward, because when I program drop, I OVS try to convert the action to count and drop. So count is for the statistic reason and to drop the packet. And for L2 forward, it tries to convert it to count and port ID, which forwarded to another port. So none of the actions are supported today. So RT flow doesn't work for these two cases. But it does work for actions like RSS, which will spread a packet to different corners. So that's the working case there. So to understand why the performance degradation or the performance difference, we are using a Windows performance toolkit called Xperf. So I think it's pretty much like in Linux, we are using perf. In Xperf, it's also pretty simple. So the step is like you start OVS and then you send traffic, and then you say Xperf start. And then you start, in the background, you start to collect all the samples and all the statistics. And then you can stop it and save the trace file somewhere, and then you stop OVS. And then you'll see a pretty nice graph about your CPU utilization, all your process, the stack, and the breakdown of all the CPU usage. So we want to compare the kernel and the DPDK case. So first, let's see OVS kernel module. So OVS kernel module, first we see on the left-hand side, it has pretty high CPU utilization. And then on the middle side, we see that, okay, this blue line is showing somewhere about 8.3. So here, 8.3 actually means 100% CPU utilization, because in our system, we have 12 cores, and it tried to get everything weighted. So 100% divided by 12 equals to 8.3 something. And then we found that, okay, this one, which uses 100% CPU, is actually not OVS-V3D. So OVS-V3D is actually using very, very low CPU performance, like on the right button, only use 0.01. So actually the one that use for 100% CPU cycle is called system. So then we can click the system, and we found that, okay, the system means the Windows kernel module, actually. So Windows kernel module, this is I think the 12 kernel thread inside the kernel. And then so it's using the 100% CPU. And then if we click into each kernel thread, it will show you that actually this is a MLX5 kernel driver that is processing the the packet. Actually, I didn't go through. I didn't resolve all the symbol, but I think at some point you can see the MLX5 driver will pass the packet according to the OVS, and OVS is busy processing the packet in the kernel. So on the other hand, for OVS-DPDK, the CPU utilization is also reaching 100%, but the characteristics, it's showing different characteristics that actually all the 8.3, all the CPU cycles are spent in Userspace or spending on the OVS v3D. So here you can see OVS v3D has several threads. So these several threads, if you zoom in, then you'll see actually they are the PMD thread main. And each PMD thread main is actually using the 8.3, the full CPU utilization. So if you click more, it will give you a breakdown of all the cores from CPU, from the PMD thread main to like process packet batch to, for example, here we can see mini flow extract spending some CPU times. So in conclusion, we know that, so actually for here, we can see OVS-DPDK spend most of the time, the CPU time in user space, because DPDK bypass the kernel and then OVS get all the CPU resources and focusing and doing the packet processing. Well, in the case of kernel modules, they are more time spent in kernel doing the packet processing. So in conclusion, in this talk, we are thinking about whether we can run OVS-DPDK on different platforms, on both Linux and Windows. And the goal is to have something called write once, run everywhere. So can we run one features, or can we write a protocol in one place and run some different platforms? So DPDK library support both Linux and Windows, and it's already a very good abstraction layer for device driver. For future world, we need to test all the existing Datapath features like tunnels, whether the same tunnel implementation in user space works on Linux and Windows. And the second one is OVS-DPDK, of course, shows very, very good, like 10 times better performance than kernel. So, but that's the packet forwarding part. So what if we need the TCP/IP stack? Then we need to inject the packet into the kernel and come back. And of course, the CPU utilization is always 100%. And we need interrupt mode support. Or hardware offload should be an ideal case. Then it will show very good performance with very low CPU. However, the number of action support is also limited. And also, we have to figure out the interface to connect OVS-DPDK to virtual machine or container. So this is also work in progress. Microsoft is working on Windows version of AFXDP and also the Windows VNIC PMD for connecting to the container using DPDK library. And also, today the PMD support is still very limited. So I try to deploy OVS-DPDK on the cloud. So far, for example, for Azure, it supports MLX5EF. AFXDP is on the way. I tested on Amazon EC2. So the only thing it works is IXGB-VF. Like ENA is still not supported in DPDK yet. For Google Cloud, most of the devices are VirtIO device, and there are patches on the DPDK mailing list, but it's still it's still work in progress. With that, I thank you for listening to my talk. This is my page. Feel free to try it out. And any question, please let me know. Thank you.
Let's thank William for his talk and his work, and let's welcome him to the OVSCon stage. William, glad to have you here.
Hi, thank you.
So we have some questions about your talk. So Frode Nordahl writes that OVS running on non-Linux OSs is pretty cool. What do you think is the main motivation for users to do so on Windows?
Yes. So I think one reason is that we see a lot of people, a lot of like Kubernetes users are deploying their container in Windows platform. So there's a separate project done by VMware called Entria, which use OVS as the CNI, the Kubernetes CNI for the Kubernetes container use case. So that's why we are thinking about, okay, since we have OVS-DPDK on Linux, and can we have the similar thing, OVS-DPDK on Windows, so that at the higher level, the Kubernetes CNI can use both. Yeah, that's one of the use case, but I believe DPDK or OVS-DPDK should have more other use case than this one.
Perfect. And then we have a couple of questions from Flavio Fernandez. So first, he has a technical question, and that is that does it matter what version of Windows you're using for adding the missing support, and specifically asks about Windows 8 and 10 and 11.
Yes. So right now, actually, a lot of low-level details, for example, like device driver, interrupt delivery, or like Windows kernel module, they are all handled by the DPDK community or Windows DPDK community part. So OVS kind of take advantage of their work because we sit on top of the Windows DPDK, right? So I believe a lot of things are depends on the support for DPDK Windows porting. So I believe right now it's only supporting Windows Server, but yeah, there should be a list, but I can share later for which version of Windows is supported or not. Yeah.
So would it be fair to say that the critical part of the support question is what versions of Windows does OVS or does DPDK for Windows support?
Yes, yeah.
Okay. And then Flavio also asks whether the fact that Windows is not open is one reason that it's better to leverage DPDK on Windows.
Oh yeah. So I think Windows is not open, right? But if you think about Datapaths, right? So right now we can add new feature in Windows Datapaths by writing like Hyper-V extension. So although it's not open, but we can still adding new feature, fix bug, or whatever, do what kind of not whatever we do, but kind of do things we want. So moving to Userspace, I believe, of course, it's more flexible and better performance, but it's hard to say at this moment, like compared to Windows kernel module, which one is better or not. Yeah, and I believe it will depend a lot on the use case for this one.
I guess the lack of openness of a lot of the Windows software means that we just don't have much insight into why it's slow, and we have no influence over it. On the other hand, with DPDK, since we're controlling the whole thing, we can control that.
Yes, I think that's a good point. Yes, I believe part of the VMware people are testing Kubernetes using Windows, and they do hit some performance issue using OVS kernel module on Windows. And most of the time we don't know how to like improve it or how to optimize it. Yeah.
That makes sense. So we do have time for more questions, but I don't see any more coming up. Do you have any final thoughts or thoughts about future work, for example?
Yes. So for future, I really want to try OVS-DPDK. So I really want to try OVS-DPDK on the cloud. So because these days it's very hard to get physical network device, and I found that cloud vendors today provide several different type of devices. For example, E1000, VirtIO, VF, from Mellanox or from Intel. So you can create a like two VM with a virtual function, and then you can start your testing, just like you have set up two physical machine and then connect back to back. However, on the cloud, you have to be aware of some firewall setup or something. So it's different experience, but yeah, I believe lots of people are deploying things on the cloud. So that's something I want to try. Try, yeah.
Well, that does sound like an interesting experiment. So I think we're out of questions.